So, good afternoon. Hello.
Good afternoon, sir.
Good afternoon. So, time check. It's already 3:32, but we'll start at exactly 3:35. So we still have 3 minutes more left to wait for the others. Okay. And while waiting, so I did mention in my announcement. I did. Did I? Let me just check. Yeah. So let us use this opportunity. If ever that you have a question or clarification regarding with our past module 1, module 2. Okay, so this is now your time to, or this is now your chance rather, to ask that concern of yours. Okay, so there is a direct message coming from Mr. Soriano. Well, turn sir, medyo malakas po ulan dito sa amin. Medyo bumabagal po net, pero okay pa naman po ngayon. Okay. So, just in case that you cannot understand some of the things that I am saying, so this meeting of ours are recorded, so you can always go back and then watch this one again on the watch video stuff. Okay. All right. So, anyone who has a concern so far? None? No one has any clarification? There is another message, but this one came from Mr. Macabio Rafael. What do you mean? End po coverage ng quiz that was due today? Pa- Ay, ano po coverage ng quiz that was due today? Today? Ano ba ngayon? Today is September 9? 7 pala. September 7. So there are only two activities which are due today, which is the short quiz and then the case study number 1. So for the short quiz, the coverage of this one is the chapter 1 itself. Okay? And the case study, so just read the facts and then the question, and then you'll be able to answer the case study number 1. Okay? Okay, so there is a question from Mr. Jen Alexis. I think it would be better if you guys will just send your message to everyone so they can also read your query. So his question is, Sir, may query po ako, yung sa may leakage po ba? Constant lang po yung current nun or iba-iba din? Different. Okay. So I will be able to talk about that later on, just a little bit more information, but not exactly the main topic. Okay, so when I say leakage current, of course, that still depends on the voltage source itself. Okay, so again, just like what I mentioned last time, if it's in reverse bias, it will not accept or it will not permit the current, right? But if you have a super high voltage source like maybe 5,000 volts, so there are some or there is a chance that uh, it will now permit a current or a voltage, okay, wherein it will completely bypass that diode since it doesn't function as a diode anymore. Okay, it's just a wire already since parang nasira na siya. Okay, wala na yung function niya as a diode itself. Okay. All right, so there are no other questions anymore. Okay. So yeah, good to know that since I don't really know how to pronounce your name, guys. So if ever that I mispronounce your name, so please correct me right away. So it's Jean Alexis. Okay, Jean C2. Just kidding. Well, anyway, so how many are we now? 10. So parang kanina 12 tayo ah. May umalis ah. Okay, so any other concerns before we continue? I mean, start rather. Since natapos pala natin last meeting yung module 2. So we are now in module 3. Concerns or clarifications, guys? Okay, so none. Okay, so I guess none anymore. All right then. So as usual, I'll just give you guys a short walkthrough, okay, about the week number 3, which is the last module, okay, before your midterm exam. So in here, this is where you can see the topic learning outcomes and then the list of topics, of course. So simply we just talk about rectifier, half-wave rectifier, and then full-wave rectifier. Okay, so those are the things that we are going to discuss in chapter 3. And then here are the, some helpful videos, okay, which explains what is a rectifier, okay, how does it work, okay, and then what is half-wave rectifier, what is a full-wave rectifier, and then what is a full-wave bridge rectifier. Okay, and then if you need more information, you can download this PDF right here. Though this one is more on derivation and how they did come up with that formula. Okay, the efficiency, RMS, okay, VRMS. But yeah, this one is super helpful if you want to know more on how did they come up with that or with such formula. Okay, and as usual, you're going to have some practice exercises right here. Most of them came from quizzes, so just check them out. So this will enhance your, or this will call that one. It will practice the knowledge that you have learned, okay, on the chapter 3 itself, okay, and then you might be able to learn more, okay, when it comes to rectifiers and then diode. So I have also some like I think this is a PDF or just a website. So this is a PDF. Okay, so it already has an answer. Okay, so number one it has this answer. Number two, it has this answer. Number three, it has this answer. So I would like you guys to analyze and then why the answer is A or B or something like that. Okay, so you will learn a lot of things in this PDF right here. And I have also found two websites wherein you can check or you can choose rather, and you can check also the y is, let's say, a is the correct one, or y is b is the correct one, or c is the correct one. Okay, so this one is quite helpful also. So there's a lot of numbers in here. It's up to 100, I guess. Yeah, it's up to 100. Okay, so just try to answer them. Okay, so bridge rectifier question and answers. And we also have here sand foundry. So it's the same. You can guess first, and then before, maybe before viewing the answer, you must have already, let's say, answered C, B, or A, or D. Okay, and then check whether you've got the correct answer or no. And if you wasn't able to get the correct answer, it will explain here why is D is the correct answer. Okay, so it also has up to 10 questions, which might be helpful also in understanding about rectifiers. Okay, and of course we're going to have 3 quizzes, but don't you guys worry, these are super easy. Okay, so 20 points, 10 points, 10 points, and then the case study is 50 points. So as you guys can see, this one is, even has a higher score than your quizzes in module 3. But yeah, so I'm pretty sure that you guys will be able to perfect all of my quizzes for the midterm, since all of them are super simple. Okay, then after that, of course, will be your midterm exam. Okay, and if I'm not mistaken, we still have 1, 2, and 3. Yeah, I think we still have 3 meetings left. So let me just check the calendar. All right, so for Tuesday, Friday, uh, your examination date is September 17th, and the is 7, so we still have 1 and okay, so there's only 2 meetings left. Okay, so 10 and then 14. So hopefully we can finish this module today. But if not, then we'll just continue it on Friday. But if we can finish it today, then I can give the September 10 and September 14 as your free time to finish all of, the activities that I have given to you guys. So the same with your other subjects. So you can use the time to finish the requirements that they are asking you to do. Okay. So, are we clear so far with our schedule? We're actually ahead of time. Okay, but just in case that you guys would like to advance, we can have an advance discussion on September 10, wherein we are now going to discuss the topics and finals. So if you guys are okay with that, then we can also go with that. Okay, so I'll just ask you guys maybe next meeting. Okay, before our next meeting, I'll just announce it and then I'll let you guys choose if we're going to have another discussion for the module 4, which is the papers. All right, so are we clear so far? Any clarification? Okay, how about the others? Only Maris Galigues is okay with that, or just fine, or doesn't have a question? What about the others? Do you guys have a concern? Hello? Are the others still around? Mr. Mark Jason, Eliana, are you here? Okay. All right. Anyway, so if you guys don't have a question, then I'm glad to hear that. So let's start now. So this is a 43 slides for a total 43 slides for the chapter 3, which talk about rectifiers. So let's start with the question, what is a rectifier? So a rectifier is an electrical device that converts alternating current, or AC, which periodically reverses direction to a direct current, which is the DC, which flows in only one direction. So in other words, a rectifier is a converter from AC to DC. So this is the initial input, and then we have this output as the DC. Okay, so this one straightens the direction of the current. So if we have rectifier, we also have an inverter. So if we have from AC to DC, we also have this DC to AC. Okay, so very straightforward. Okay. And let's now talk about the types of rectifier. So in here we have half-wave rectifier, we have full-wave rectifier, and then the bridge rectifier. So I miss the other one. We have the center tap rectifier, which is also under the full-wave rectifier. Okay. Anyway, let's start with half-wave rectifier first. So in here we have this sine wave, or we have this input. Okay. So VI stands for the voltage input, VM stands for the maximum voltage or the peak voltage. Okay, and then the T right here is the time. Okay, so of course, as time goes by, okay, we have this portion of time where it's positive, and then we have this portion of time which is negative. Okay, so it doesn't overlap with each other. We're in here for this specific time, which is t divided by 2, we only have positive uh, output. Okay, and vice versa. After the positive output, it will reach this 0 voltage right here, and then it will now create a negative voltage. Okay, so this is an example of a circuit wherein you'll be able to have this kind of output. Okay, or this one is the default circuit when it comes to half wave rectifier. Okay, so yeah, that's it for the half wave rectifier. So let's have another uh, representation of half wave rectifier. So we have this circuit right here. Okay, so as you guys can see, this is a diode. So let's just say that for now it's an ideal diode, and then we have the voltage input right here, which is positive, and it's connected to our positive. Okay, and the negative is connected to negative, which will make this one as a closed circuit. So as a result, it will become like this. Okay, so we don't have the voltage threshold, we don't have the bulk resistance, since again, this is an ideal diode. Okay, and as a result, this will only accept positive cycle. Okay, and of course, this will be the result of that one. So as it names, its name trying to say, we only have a half wave uh, graph right here, or a result, okay, which is the positive cycle only. Okay, so what is this t divided by 2 and then going to t? So it is the time that it will pass through the negative cycle. Okay, so initially, of course, it will have a positive input first, and then after that time, it will reach 0, and then it will now have a negative input. So at that negative input, of course, if we have this negative and then connected to the positive, we're going to have a reverse bias connection in this diode. So as a result, we'll be having an open circuit. And as you guys can see, if it's an open circuit, so there is no flow of current. So as a result, we have the 0 voltage in here. So it's just a flat line. And then it will wait again after the time of negative cycle. Then after passing through this 0, and then it will now increase for the positive cycle. Then it will now, give you uh, another voltage output. So as a result, we have positive, 0, positive, 0, positive, 0. So as its name trying to say, it's just accepting half wave of the voltage input. Okay. So during the period t divided by 2 going to the t, the polarity of the input signal Vi becomes negative, which causes the diode to turn off, resulting in an open circuit equivalent across the diode terminals. So if you're going to compute the VO, so VO is equal to I times R, but the current is 0, so 0 times R is equal to 0 volts. Okay, so are we clear so far up to this point? And why do we have this kind of graph?
Yes, sir.
Okay, right. So let's now talk about the what's VI, VO, okay, and then the complete graph of that one. So initially, of course, we have this input. We have the positive, negative, positive, negative. So it won't miss a cycle since this is the AC source. Okay, but once it passed to a certain circuit, let's say this happy rectifier circuit, it will give you an output or the VO, something like this. Okay, just like what I mentioned a while ago. And then this is one cycle. Okay, the positive and then the negative, which is the flat line. Okay, So one cycle, another cycle, another cycle. Okay. And then this VDC right here is equal to 0.318. Okay, so this is the average, okay, voltage that you will get if you have a half-wave rectifier. So this will never change. Okay, so by default, that is the VDC value, which is 0.318 multiplied to VM, okay, or whatever is your peak voltage in here. Okay, so again, VM is our maximum voltage. So that VM is this peak right here. Okay, so that depends on the voltage input. So if you have the voltage input of 20, then this one is 20. Okay, so let's now use a silicon diode. Okay, so as you guys can see right here, just focus your eye on the left side part first. So I mentioned last meeting, okay, that if we have a diode, so it will always consume a certain amount of voltage. So in a silicon, it will consume 0.7 volts. So if you guys are going to take a look on this one, it's not going to, going to go up from 0 to going to its peak voltage anymore. But instead, it will start only, raising its current if it's already at 0.7 volt voltage right here. So at 0.8, then that's the only time that it will permit a current and then will flow right here. So the same at this point, okay, with the negative cycle. So it will consume, or not really consume, but it will be added rather. Okay, it will be added to the uh, let's say second waveform, okay, or the half waveform, okay. But since in reverse bias, now we don't have a complete or we don't have a current that is uploading on that circuit, so we don't have an effect on this half cycle or the negative half cycle. So it will only affect the positive half cycle. Okay, so this is now the actual, okay, output of that one. So your VM minus the voltage threshold, which is negative 0.7. Okay, so before it's just align, since it will make this one a closed switch, but in here we now have to consider this voltage threshold, which is 0.7 volts. Okay, so while the diode conducts during the rectification process, it generates a DC output that carries the fixed voltage level for the voltage difference. Okay, so in other words, your VO is equal to VI minus VT or VM minus VT. So that's how you compute the voltage output. Okay, and thus VI should be greater than VT. Okay, so it's already common sense. You must have a higher voltage input or a voltage source than your voltage threshold, because if not, then you won't be able to use this circuit completely. Okay, if you only have 0.6 and below, if it's the silicon. Okay, so you can call that one as VI or VM. So they are just the same. So VI is the voltage input, and then VM is the maximum voltage. Okay. So the average DC output formula with the threshold voltage of the diode is again this one. So it's approximately 0.318. Okay. So if it has now a voltage threshold, then you have to deduct that one. Okay, so VDC is equal to 0.318 times the peak voltage minus the voltage threshold. But if it's an ideal diode, where is that one? If it's an ideal diode. So if it's an ideal diode, like this one, so you don't need to like deduct the voltage threshold. So just multiply that one to VM. Okay, no need to deduct the voltage threshold since we don't have a voltage threshold in here. Okay, but if it has now a voltage threshold, then you have to deduct that one to our VM. Okay, and then whatever is the result, that is our uh, DC output or the average voltage. Okay, so are we clear so far up to this point?
Yes, sir.
Okay, how about the others? Okay, great. So if ever that you have a question, again, just speak right away. Okay, and then we'll talk about your constraint. So let's have an actual example. So example for half-bridge rectifier, problem number one. So it says here, consider the diode as an ideal diode. So again, if it's an ideal diode, then if it's in a forward bias, then just make that one as a wire, okay? Or just make this one as a closed switch. So we have this voltage input. So this is an AC input, of course. So we have 20 volts peak to peak. So positive 20 and then negative 20. Okay, so this one is one cycle. And we have this connection right here. So positive connected to negative, negative connected to the positive. So for the initial input, as I can already see, it's already super obvious. For the positive side, it won't conduct a current since positive connected to negative, negative connected to positive. This will become a reverse bias. Okay, so as a result, we have a zero voltage output for the positive cycle. But for the negative cycle, so just interchange those two. So we now have negative right here and then positive right here. So negative connected to the negative, positive connected to the positive. So it will now conduct a current. So as a result, we now have a result on the bottom, which is the negative half cycle. Okay, so here is the solution. And here is the graph, by the way. So again, it won't accept the or it won't permit the positive cycle, but it will only permit the negative half cycle. So right here, right, and then right here. And then this is the computation for the voltage output. So it's super obvious since this is just an ideal diode. So after passing through this wire right here, it's still 20 volts, okay, across this voltage or across this resistor right here. Okay, and then for the VBC, so this one will become negative since we have a negative half cycle. So just remember that one, if it's a negative half cycle, then you must make this one negative also, since of course the average must be negative also since we have a negative output. Okay, so if it's positive, then make this one positive. So again, by default, we have 0.318 times Vn minus Vp, wherein Vp is, of course, 0. So 0.318 times 20 is equal to negative 6.36 volts. Okay, so that is the average voltage that you can get if you have this kind of input, 20 volts. Okay, so are we clear so far regarding the solution for the problem number one?
Yes.
Okay. So again, if you have a question, just speak right away. Okay? Huwag mo nang patagalin pa para agad-agad masagutan na natin kaagad yan. Okay, so let's have another example, example number two. So problem number two, solve the problem number one, considering the diode as a silicon. So before it's just an ideal diode, but right now, we now have to consider the voltage threshold of a silicon. So again, a silicon will consume an amount of 0.7 volts. So the same question, evaluate the output BO and find out the DC magnitude of the output for this circuit design. Okay, so we still have the same input, the same circuitry, but we just have to consider the voltage threshold and then the same output, of course. Okay, so I'm sorry, just tweak this one or just change this one. So it's not 20 volts anymore. Okay, so in here, just deduct the voltage threshold. So the peak voltage that you will get or the BO that you will get right here is now 19.3. Okay, so it's very obvious. Just deduct the voltage threshold. So Vm minus Vt is equal to 20 minus 0.7, and this is now 19.3. But yeah, not 20 anymore. Okay, I just wasn't able to find a simulator which has the same result as like this. So that's why I wasn't able to change this one anymore. But yeah, this one is 19.3. Okay. And then for the VDC, we just have an additional, so it's negative 0.318. And we now have 20 minus 0.7. So before it's just minus 0, but we have to consider now the voltage threshold. So we have negative 0.318 times 19.3 will give us a result of negative 6.14 volts. Okay. So let's just discuss, what if we have a, uh, let's say, a voltage threshold, and then what if we have a voltage threshold? Did I say it right? What if we don't have a voltage threshold? And then what if we have a voltage threshold? So that's the one that I would like to say. Okay, so this is the value for the first example. So we've got a VDC of 6.36. And then for the second example, we have a negative 6.14 volts, wherein difference of those two is 0.22 volts. So the drop in the output DC voltage due to the 0.7 volt factor is around 0.22 volts, or approximately 3.5%, okay, of the voltage itself. So if, in reality, okay, because a, a diode always consumes a voltage, so just expect that you will have a 3.5 percent loss of voltage after passing through that diode. Okay, well, if it's a silicon diode, then it's 3.5%. Okay, so but mostly, yeah, we already consider it's already a fixed value of 3.5%, even though it's in germanium. Okay, just to make it safe, and then to to avoid the hassleness of computing. Okay, like if it's germanium, then you have to recompute that one, but let's just stick with 3.5%. Okay, or the this, if you want to get the exact value, just calculate, okay, if you have a voltage threshold or if you don't have a voltage threshold. So by the way, it will give you the same result. Okay, so it will never change. This will be always 0.22 volts if you're going to use a silicon diode. Okay, so that's pretty much it for the half wave rectifier. So let's now move on for the full wave rectification or full wave rectifier. So as its name trying to imply, so this one now accepts positive and then the negative cycle. So it's now a complete cycle. So when an AC sinusoidal signal is used as the input for rectification, the DC output can be improved to 100%. So half wave will only give you 50% of the result, but this one will give you 100% result level using a full wave rectification process. So how do we do that one? Okay, so all you need to do is come up with this kind of circuit, okay, which is called the 4-diode bridge rectifier. Okay, so if you have this kind of circuit, then you can now pass through uh, a complete AC cycle. Okay, and then you can also have a complete AC result or AC voltage output. Okay, so let's have this one as an explanation on how this one works, how this 4 diode bridge rectifier work. So when the positive input cycle progresses through the period t is equal to 0 to t divided by 2. So from the start up to the uh, half cycle, the polarity of the input AC signal across the diode and the output from the diode are as represented below. Okay, so if we have a positive cycle, let's just say the half cycle first. So we have positive connected to the positive, and then positive connected to the negative. So it's already obvious. So you must have the correct, polarity for you to be able to make those diodes work. So positive is connected to the positive, so this will turn on the diode. But the other one, positive is connected to the negative. So as a result, this will give us, an open switch or an off diode. So after passing through this diode, so you are now at this point. So you now have to choose either this VO right here or this diode right here. Okay, so let's just assume that it will split into two. Okay, but if you guys are going to take a look on this one, we have let's say this is the positive one and then this is the negative one. So it will give us a result of a reverse bias on this diode. So as a result, it will go back right here and then will now flow on this DO. Okay, so from here, it will pass through here, going back here to this another diode, and then we'll go back to the voltage source itself. Okay, so in other words, we have a like a zigzag connection. So from here to here, let me just change the color. So it is from here to here to here, and then here, and then here, going back there. Okay, so that is the positive cycle. Okay, so at this point, of course, it or the half cycle or the positive half cycle are now ended. So we're now going to proceed to the negative half cycle. So this one now will become negative, and then the other one will become positive. So as a result, let's just change this one into green, maybe negative and then positive. So if we have a negative and then positive right here, so this negative is now connected to this negative diode or negative part of the diode, and then positive is connected to positive. So this will turn on the diode, and then negative is connected to the positive, and then positive is connected to the negative. So this will turn off the diode. Okay, so as a result, the negative half cycle will now flow right here. And then the same scenario with this diode right here. So it won't be able to flow on this connection since this will become a reverse bias. Okay, so from here and then here and then going back to our voltage source. Okay, so